Hey, what's up, Chem Peeps? This vid, we're just gonna drive home the fact that in weak acid solutions, the concentration of hydronium ion is much less than the concentration of your original weak acid. And we're gonna use an ice table to illustrate that. Something that at this point you should know and love. And recognize that it's gonna be something that we use a lot in this unit on acids and bases. Alright, so we're asked to find the hydronium ion concentration of a 0.100 molar hydrocyanic acid solution. We're told the Ka of HCN is 6.17 times 10 to the minus 10. Now, I know that the hydronium ion concentration is going to be far less than 0.100 molar because it is a weak acid. But how do I find out numerically what that value is? Ice table time. First, my reaction for HCN in water. Boom. Ice table. Boom. Gonna immediately drop my water because it's a pure liquid and I don't want to confuse myself. Initial concentration of the HCN is 0.100 molar. Initial concentrations of hydronium ion and cyanide ion are each 0. I'm gonna think about the change stoichiometrically based on the coefficients in my balanced chemical equation. Minus x plus x plus x. And then combine initial and change to determine what the concentrations will be at equilibrium. Boom. Now, we're looking for the hydronium ion concentration. Essentially, we're looking for x. To do that, I'm going to set up my Ka expression. And you should always, always, always do this in terms of the species that you have in your reaction first. Don't just plug in the numbers. Boom. Now that we've written it in terms of the species that are in the equation, let's write it including our equilibrium concentrations and the value of Ka. We're told in the problem that the value of Ka is 6.17 times 10 to the minus 10. Much less than 1, we would expect that with a weak acid. That's equal to our equilibrium concentrations of hydronium and cyanide ions over our equilibrium concentration of HCN. Okay, now, an important step to make here. Recognize that the initial concentration of my weak acid and Ka value differ by a factor of 1,000 or more, in this case much greater. And because they differ so much, even though the HCN concentration is going to decrease, it's going to decrease by such a small extent as to be insignificant. And so we're going to make an x is small approximation. But never just scratch the x out and move on. Be explicit in your free response that you are making that x is small approximation because the initial concentration and Ka are vastly different. X is small approximation can be made because initial HCN concentration, that's what little sub-zero means, and Ka differ by a factor of greater than 1,000. Boom. Be explicit, be clear. Don't just scratch it out and move on. Now, that's great because it simplifies our expression to 6.17 times 10 to the minus 10 is equal to x squared over 0.100. All right, now let's jump to our calculator. Parentheses, 6.17 second e, negative 10, close parentheses, times 0.100, enter. Second square root, second, enter. X equals 7.85 times 10 to the minus 6 molar. Remember, X is our hydronium ion concentration. Boom. Be comfortable with calculations like this. You'll be doing it a lot this unit.